Okay, so let me just quickly recap what we did last time. Last time we learned about estimating or roughly plotting the magnitude response and phase response of an LTI system with the rational system function, or means for an IIR, primarily for an IIR system, that how by looking at the pole zero plot, at least you can comment easily. We saw that commenting is very simple. Looking at the location of poles and zeros, you can comment, and actually you can calculate. And how you do that? You plot the pole vector and zero vector on the unit circle. So first you need to plot all poles and zeros, then plot these vectors on a particular value of omega, multiply the length of all the zero vectors together, and then multiply all the lengths of pole vector together, and then divide them. That will give you the magnitude of the frequency response at that particular frequency. Then you keep moving the frequency, keep moving these vectors, and for example here it will be length of this vector, and divided by length of this vector is 1. So it is in this case just length of this vector. So and you know that as you get closer to the unit circle, so at the location of the 0, you will have the minimum length. So it will have minimum frequency response. If it is in dB, it will be something like this. And once you move exactly away from this, it will have the maximum frequency response, which is shown here. So exactly 180 degrees away from this, you will have the maximum magnitude response. And similarly, you can plot the phase by actually calculating this angle, the angle of the zero vector and the angle of the pole vector. Okay, so at this point is this angle. Once you are here, so it is this angle into this angle, which is omega. So by moving on the circle, keep calculating phi and omega, and calculate the phase response. So both can be calculated. And so this is an example where we said, okay, just keep moving, and keep calculating this. So it's a simple graphical technique. This example here, I know for sure that there are going to be 3 dips where the response will go to 0. So location of 0, if zeros are exactly placed on the unit circle, I'll dip to a unit circle, and the poles are closer to the unit circle, your response will go up. So if you want to lift the frequency response, you move your poles closer to the unit circle, because it is 1 over this value. So, and they are automatically, will learn about the algorithms where the algorithms itself will place poles, but they are placed in a fashion that the frequency response will remain flat from 0 to this frequency. It will remain flat, and then it will dip. So the placement of 0 here will bring the frequency response down as quickly as possible. Okay? So this is the response. So it remains almost flat, and then it bring it down, keep it down, right? So it bring it down, then it again moves up, keep it down. So this is how the algorithm for filter design will place. Otherwise it's a difficult problem to solve in placing poles and zeros to shape a frequency response, but there are algorithms which will help you to do that. This is again something which we saw, the frequency response and the phase response. This is how again you do this: plot all the zero vectors and plot all the pole vectors, and then do the math. Here all these are the zero vectors, all 1, because all zeros are here at 0. So then you need not to worry about the zero vectors, only about the pole vectors. So there's a pole here, a pole here. So if you are computing here, the length of this. So 1 divided by V1 over V2 will give you the, and in this case the V3 is 1. So length of V1, length of V2. There are 2 V3s, but both are 1 because zeros are at the origin. So then this is yet another example where you have 3 poles and 3 zeros. Zeros are on the unit circle. So this is how you compute. So keep computing this value, and you can just, by knowing 3 zeros, there will be 3 dips. 3 dips in this. So this is, you compute, as you can see, you hit this 0, you get this dip, and similarly you do that. And this is so once you plot h exponential j omega, our interest is in finding the magnitude h exponential j omega and the phase of this, which is angle h exponential j omega. And usually the plots are on dB scale, so you take log base 10, 20 log base 10 of h exponential j omega. It gives you finer resolution in the stop band. That's what you want to see, that in stop band how your filter is behaving. So it gives you finer. Otherwise, if you look at this in absolute or absolute magnitude plot, it will not show you these. It will simply show you this almost 0. So magnitude, just simple magnitude plot will not reveal a lot of these details. So that's why dB plot is usually preferred, that it gives you more insight into the stop band, because you really want to see the stop band, how the stop band is. And then phase is just the angle h exponential j omega. And the group delay we know is the negative derivative of this. A group delay is also important. So you need to have the magnitude plot, the phase plot, and the group delay. Usually, you don't care about phase plot, because group delay is a better representation of phase distortion. So usually you care for this and you care for this, the phase distortion. So then once you know h exponential j omega, if it is in dBs, you know that the multiplication is addition in log. So the multiplication is turned into addition, that if you take 20 log base 10 of x and 20 log base 10 of h, then the magnitude responses they add and their angles also add. Otherwise they multiply. Okay, otherwise they multiply. But if you take log, we know log of two things which are multiplying, you can replace them by log of this plus log of this. So this is, again, our interest is in finding a 20 log base 10 of y, and this is how it is related. It's a log magnitude response in dBs. So this is we already covered like 3. Now we come to the next topic, which is, I'll quickly just go over the all pass system, and then we'll start learning about all pass systems. Are sometimes important, though they all pass means they'll pass everything there, because the magnitude response is 1. So all pass system is a system where minus pi to pi magnitude response is exactly 1. So a question is, why do you need an all pass filter? Because it's not going to alter any frequency quantum. All pass filters can change the phase. So usually you can use an all pass filter to change or to compensate for the phase distortion. You say, okay, this IR filter is causing this phase distortion. If I place an IR filter, it will help me to cater for the phase distortion. You use it for that. And sometimes you know that if, let's say, there is in inverse system, there is a pole that is outside the unit circle. There's a pole which is outside the unit circle, and you don't like it because you know that is an unstable system. So you put in cascade an all pass system with it, and that all pass system has a 0 at the location of the pole. Okay, if you have a 0 at the location of the pole, then pole 0 will cancel out. Okay, and its corresponding pole will be at 1 over a. So if it is outside, 0 is outside, the pole will be inside. If pole is outside, 0 will be inside. So you can also compensate for something where the pole is outside. So you can do that. Either you make a minimum phase system, or you put this with that, cancel out the poles and zeros, and design. So all pass system is a system where if a pole is at A, then the 0 will be at 1 over A complement. So what is, or conjugate, what is the conjugate? If let's say pole is at 0.2 plus 0.2j, okay, if pole is here, then you take 1 over A, it is 1 over 0.2 minus 0.2J. So, and then you take its conjugate, so plus and minus. So then there will be, if your pole is here, then there is going to be a 0 at this location. Okay, and 0 at this location means you multiply it with 0.2 plus 0.2J divided by 0.2 plus 0.2J, right? Because you want a real part and an imaginary part. This multiplied by this will give you something in the denominator which will be smaller than 1, so will make this bigger than 1. So a pole here means a 0 somewhere here outside the pole. So if you have a 0 here, its pole will be here. A 0 will be outside the unit circle and pole is inside the unit circle, and this is the relationship A and 1 over A. A simple example is, if you don't worry about the complex, that let's say you place a pole here at 0.5, it is a real pole, so where will be a 0? 1 over 0.5, which is at 2, so a 0 will be at 2. So this is an all pass system. If you plot its magnitude response, it will be 1. Okay, it will always be 1. So this is an all pass system. So yeah, and this is useful. An all pass system is useful because it's not going to change the magnitude response. So you can place some poles and zeros to your liking. If they can cancel out something, especially a 0 here, can cancel a pole at this location. So if you put a system, you have a system h of z which has a pole which you don't like, and you want to cater for this pole. Okay, and you say, I don't like this pole because this is outside the unit circle, it's making everything unstable. So you put an all pass system, you say, okay, let me put this here, but to cater for this you need to place a pole at here, so you say 1 minus 0.5 z inverse. So you can cancel these two out. So there will be other terms, but you cancel a pole which is outside the unit circle because of not design, but because of you are designing an inverse system, and the original system has a 0 outside the unit circle. So you can always do that. So all pass systems again are easy to understand. They may be a single pole single zero system or multiple pole multiple zero system, but every pole of an all pass system will have an accompanied 0, and that will make the total response equals to 1. Remember, the pole vector and 0 vector, make sure that it is always 1. So therefore every pole there is a 0 which is making sure that your magnitude response remains 1 throughout the frequency range. And this is what it boils down to, that a pole at A will have a 0 at 1 over A magnitude. So an all pass system is the system. Then we need to, and as I जी sir. जी
वो जो सिस्टम होगा तो
cascade होगा. The question is, if you are doing this, you need to place a system cascade to the original system. ठीक है ना? Because the two systems in cascade, then you can multiply their h of these together. Achha, then I said, okay, because the problem with an IER system is the phase distortion. Okay, so usually if people don't prefer FIR system, it is mainly due to the phase distortion, and stability is also a criteria because you need to worry about stability and all that. But phase is an important factor to consider, and people say, okay, why not to design an FIR? Though you can always design an FIR filter where you have phase distortion. Okay, FIR filter can have phase distortion too, but then there is no point in using FIR filter. Okay, so the point in using FIR filter is that there should be no phase distortion. That is why you intend to use FIR filter. So anybody who designs FIR filter makes sure that there is no phase distortion. And we have already learned what do you need to do to make sure there is no phase distortion. You design a real and even Remember, a real and even sequence will have a real and even Fourier transform, means no phase in it. So a real and even will have a real and even response, which will be all real. A exponential j omega, there will be no j in it for sure. So you design a real and even by doing this, and then you move it to make it causal, and once you move it, there will be an exponential term. You say it's a linear phase system. So linear phase systems are usually symmetric around a value because they are being moved. Okay, so this is a linear phase system where you have a magnitude term which is real and an exponential minus j omega alpha. The phase will appear as a shift minus j omega alpha. The phase will appear like this. So that once you take the derivative of it, so minus derivative of omega will give you alpha, which is a constant. So you want a constant phase, a constant group delay. So you want a constant group delay alpha. Okay? Impulse response, and this will require your impulse response to be symmetric about 2 alpha. So if alpha is integer, and it will be non-symmetric, still it will obey this if alpha 2 alpha is not symmetric. Means that this is an example. So if you ignore minus 5, this sine 0.5 pi over pi is a symmetric. It's a symmetric function. It's an even real and even function. So it's a real and even function, and we are saying, okay, this is a real and even function, this is good, and I can shift it by 5 or 10 or whatever. So if this is 5 and 5, okay, minus 5 and minus 5, so it is what is shown here, that starting from, then you really have to truncate it, but it's not being truncated, just to show you that it's at 5. Okay, so this is a good example where this is an integer, a 5. An integer, this may not be an integer. This may not be an integer. This may be something 0.5. Something 0.5 will make this. Okay. Something 0.5 is this, 4.5. What is 4.5? It is still symmetric. Right? If you look at this, it is sine 0.5 pi n minus 4.5 n minus 4.5. It is still symmetric. Symmetric is what? This sample is equal to this sample is equal to this sample is equal to this. This is still symmetric. It will have a real and even, and then you move, you actually write the form. Instead, one way of thinking about linear phase system is that first you design a real and even, and then you move. Okay, this is one way. The other way is, let's not worry about move. Let's write an expression like this. Okay, this will also be a linear phase system, that you say n minus 4.5. Obviously you cannot move something to 4.5 in digital domain, but given this formula you can always plot it like this. Okay, given this formula, I'm not moving, and I'm not saying first draw a sink and then move. I'm saying draw this. So this is real and even. So this is real and even, so this is also fine. This will give you a linear phase system. This is yet another example where you are moving it by 4.3. Okay, but 4.3, the problem with 4.3 is now your samples are not symmetrically placed. So usually this is not done. Okay, you try to, and I'll tell you why, but you try to make your coefficient symmetrical. Either they should have symmetric or anti-symmetric coefficients, and we'll see all these classes. So there is yet even, you can say that phase, though this will help. If you take a negative derivative of this, it will give you alpha. But even if there is a constant term like beta, still if you take derivative minus d over d omega, what will you get? Plus alpha. So this is also linear phase. So any system which has a phase like this is called generalized linear phase system. Generalized linear phase. If you don't have a beta, it is linear phase. If you also have a beta term in the phase, it is called generalized linear phase. Okay. So what we are getting at? We are getting at to an H. I am saying try to, if you are designing an FIR filter, always try to get a frequency response H exponential j omega which is equal to something which is real. Okay, which is real, which is just the magnitude term. And with that, the phase term may appear like this, minus j alpha omega plus beta. This is fine. Okay. If this is the phase term, this is still a linear phase system. Okay. So in FIR filters, we always try to have a system with this frequency response. Always. Okay. So this is a minus alpha omega terms, means that all frequencies are shifted by this is linear phase. Linear phase means the entire signal is a shift by this much amount, and beta means that all frequencies have this constant phase. So you can have a frequency response which obeys the generalized linear phase, which is this. Okay, generalized linear phase allows a constant phase shift beside a constant delay. This is the difference between a linear phase and a generalized linear phase. In a generalized linear phase, you also have this beta term. Okay. So I'll give you a few examples, but you always try something which is real, okay, and with this phase, exponential minus j omega alpha minus beta or plus beta, it does not matter. So it will have a constant group delay. So these are the classes of this filter. The classes are, and I'll show you in MATLAB, so go and see these things in MATLAB, that you always try to have an h of n which is symmetrical about a value. Like every h of n should accompanied with another h m minus n. Okay? So means that if you are designing an FIR filter, you need to have, you design it in a way that it falls in one of these categories. That a sample in impulse response here should have exactly same sample here. It is symmetrical. A sample here should have a sample here. A sample here should have a sample here. So this is m, this is 0. So 0th sample of h of 0 should match to h of m. This will guarantee that your system is a linear phase system. Right? H of m, h of 1 should be h of m minus 1. Okay. So this is what this expression says. H of n should be h of m minus n. H of 0 should be h of m. H of 1 should be h of m minus 1. Similarly, you just keep doing. Now there are two classes in this. One is if m is even. If m is even, what do you get? And I will shortly find out why this is important. M even means that 0, 1, 2, 3. Okay? M odd. M odd is this case, 0, 1, 2, 3. M is odd means that there are even number of samples in the impulse response, because it runs from 0 to m. Okay? So m odd means this, that this sample is equal to this sample, so every sample will be paired with another sample. But if m is even, then what do you expect? Let's say m is even means running from 0 to, for example, 4. So first sample 4, 4, 1, 3, there is an extra. So there is no pair for sample at 2. So it can be a unique sample. Right? So this is, if m is even, you have odd number of samples. You have odd number of samples, so you can pair all of them except the one in the middle. So you can have a filter like this. Always you need to, whenever you are designing an FIR filter, it must fall in one of these 4 categories for it to be a linear phase filter. Okay? For it to be a linear phase filter, it must always fall into one of these 4 categories. Then you need not to worry about the linear phase. It will always have a linear phase. Second is h of m minus n is equal to minus h of n. Again 2 types. M even, M odd. We call this type 1, type 2, type 3, type 4. So the other is that if you have a sample here, you need to have a sample here. Okay? If you sample here, this is the for 0, 1, 2 and 3, and if you have 4, a sample here, a sample here, sample here, a sample here. is what you need to have. Okay, because this got to be 0. Why? Because this should be equal to its negative, and this only 0 which can be equal to its negative, otherwise you cannot have this. So they got to be 0, this sample got to be 0 if it is even, m is even and it is antisymmetric, this got to be 0. The central coefficient must be 0 because it got to obey this, which says in that case h of 2 should be equal to minus h of 2. And the only way this is possible, that you need to that should be 0. Okay, so these are the categories that your filter must fall in one of these 4 categories for it to be a linear phase. So you can draw anything, if it obeys this, guaranteed it will be linear phase. In FIR filter, because the phase is a concern, so we always design a linear phase system. So let's see a type 1 filter. Type 1, we know if m is even number, this is the filter, a symmetric filter. Example is this, all 0, 1, 2, 3, 4, 0, 1, 2, 3 and 4. This is a simplest example. This is a type 1 FIR filter with even, m is even and odd number of coefficients. Right? If you take its Fourier transform, take it symmetric around 2, we know that, and we know how to take its Fourier transform, right? Just use the formula, take its Fourier transform, this is the Fourier transform, then do the manipulation. We know how to do that, just 5 over 2 exponential minus j omega 5 over 2 into exponential minus j omega 5 over 2, do that. So this is the real part, and remember here is the phase, linear phase, so it will always be something like this, a linear phase with 2 because it is shifted by 2. Right? So this is 2 means that it's a real part will get on one side and the phase will be a linear phase on the other side. So you can try anything, it will always fall into this category, right? Because it is around 2, so you will find this factor here. Then is an example where, so alpha is 2, beta is 0 in this case, we know. Then here is an example where you say 0 to 5, 1, 2, 3, 4, 5, okay, 0 to 5. This is a type 2 filter. Type 2 filter for 0 sample is equal to 5, 1 equal to 4 and 2 equal to 3. If you again compute its Fourier transform like this, break it down into 2, break it down into 2, you get this. So here alpha is 5 by 2. Alpha is 5 by 2 and beta is 0. This is the plot. Okay? It's a linear phase and this is the plot. You see this because whenever it goes down, it means it's changing the phase. So at this location, at this location a negative phase is marked by a change in phase. You go up by the same amount, then you go down, you hit another 0. A 0 means that you are going down and up and down and up, and you change this phase like this. Okay, so beta is 0 and alpha is 5 over 2. Now type 3 filter. In type 3 filter, you have h of minus h of m minus n. It should be antisymmetric, where m is an even number. Here an example is taken where you have this and this. Okay, this is 0, minus 1, 1. This is an anti-symmetric with m is even, means there are odd number of samples. Okay, so here you find a j pi by 2. There is no alpha in it. Alpha is 0, but beta is 90 degrees. This is just a constant term. Okay, but if you shift it, that will come into picture. Because it's not non-causal, but once you shift it, there will be an alpha which is equal to 1, and there will be a beta which is equal to pi. So there is a phase in this pi by 2. J pi by 2 is a constant phase. This is still a linear phase system. Okay, there's still a linear phase system because once you take its derivative you get 0. Okay, so this is an example where it's a type 3 filter, remember, antisymmetric. Similarly, M may be odd, and you can create an example for this as well. But this is important, that what is the consequence of symmetry? The consequence of symmetry is that you are saying h of n, h of n should be equal to h of m minus n, right? This is what symmetry means for type 1 and type 2 filter. It means if I take Z transform of both sides, they should be equal, right? If I take Z transform of both sides, in case of a linear phase FIR filter, they should be equal. Okay, take Z transform. G transform of this is h of n, Z of minus n. What is Z transform of this? If you look at this expression, h of m minus n. First thing you note is it is minus n. So if Z transform of h of n is h of minus n will be, right? यही होता है ना. अजान कर Okay, so taking Z transform of h of m minus n, I know h of minus n is h of Z inverse. Remember the property of Z transform which says if you flip n, you flip Z, you make it 1 over Z. So this is fine. Now it is shift, flip and shift, replace n by n minus m. So if you replace n by n minus m, you multiply it with Z minus m. So it means h of Z is actually equal to Z minus m h of Z inverse. So this is, it will obey this. If a system obeys this, it will obey this. You can try it out. Let's say this is your filter, 1, 2 and 1. Okay, what is the Z transform of this? 1 plus 2Z inverse plus 2Z minus 2 plus. Now do this, replace h of Z by Z inverse. If you do that, what is h of Z inverse? 1 plus 2Z plus 2Z square plus Z cube, right? Now do this, Z minus m. What is m? Minus 3. So minus, what do you get? Z minus 3, which is this, plus 2Z minus 2 plus 2Z inverse plus 1, which is same as this, right? It will always obey this. Why should we care? Why should we care that it obeys this? We should care because the 0, what is the 0 of h of Z? Remember, it is an FIR, so you don't worry about the poles. 0. If, what is a 0? At 0, the h of Z naught should be what? If there is a 0, if this is 0 of the system, and I put this in the expression h of z naught, what should I get? Anybody? No? 0, it is 0. So if there is a 0, what should I get? H z naught. 0. Where's a 0, you know? So if you have a 0, let me give you an example. Let's say this 0 is at 0.5. So what is h of z? H of z of a system which has a 0 at 0.5 and a pole here. It is 1 minus 0.5, the inverse, right? This is a system with just 1 0 at 0.5. Okay? Now put z is equal to 0.5. What will? It is, if z is 0.5, it is z inverse, it will be divided by 0.5. So it is 1 minus 1 is 0. So 0 is in fact the root of the polynomial if you put the numerator equal to 0. That is what a 0 is. Okay? So at 0, your h of z will be 0 for sure. No question about it. At 0 means that, 0 means h of z is 0 at 0. Okay? Pole is that h of z is infinity at pole, because it is root of the denominator. Okay? So if this is the 0, which is, so this says that it will obey this. It means a 0 of this will also be a 0 of this. Okay? Means a 0 of h of z, if z naught is a 0 of the system, this is important. For a linear phase, if z naught is a 0 of the system, then 1 over z naught will also be 0 of the system. This is because of symmetry. This tells us that if z naught is a 0 of the system, then 1 over z naught will also be 0 of the system. Okay? What does it mean? It means that if in a linear phase system you place a pole here at 0.5, if it is a linear phase system, there will always be another pole, a 0. If this is a 0 at 0.5, there will always be another 0 where? 1 over 0.5, always. Okay? 1 over 0.5 is what? 2. So they will always, guaranteed there will be a 0 here too. Okay? The interesting is, there, if there is a 0 at here, 0.5, let's say. 0.5 plus 0.5j. If there is a 0 at 0.5 plus 0.5j, there will always be a 0 at where? 1 over 0.5 plus 0.5j. What is this? This is because you say 0.5 minus 0.5j divided by 0.5 minus 0.5j. Okay? So there will be a 0 at, so you compute its magnitude, you will find out there will be a 0 at here. For this 0, there will be a 0 at this point, because this you need to compute the magnitude, 0.5 square. Okay, this is a plus b, a minus b, so a square minus b square. So it is 0.5 square minus j square is minus 1 plus 0.5 square. So it is 0.5 square. 0.5 square is 0.25? 0.25. Ji? 0.5 आ गया. So 0.5. So 0.5 is what? So it's G. 1 minus 1 J. So you go. Okay. So if you have here, you go here. 1 minus 1 J. So a 0 here means a 0 here. Okay. A 0 here means a 0 here for sure. But we also know that if you have a 0 here and your h of n is real, if you have a complex 0, then complex 0 must always have a complex conjugate. Let me draw it here. So this is interesting. And to summarize, if it is a linear phase system, okay, if it is a linear phase system, a 0 here always means a 0 here. A 0 at z naught must have a 0 at 1 over z naught, number 1. Number 2, that if it is also real, because we are not interested in having an h of n which has complex coefficients. If it is real, then a 0 here always means a 0 at z naught conjugate. Okay? If you have a 0 at z naught conjugate, then there must be another 0 at where? 1 over z naught conjugate. Must. So a 0 here means you already know 3 zeros. If I place a 0 somewhere, I know not just 1 0, I know 3 more zeros. Always it will happen like this. A 0 here will have a 0 here, 0 here, 0 here. Okay? This 0 is because the h of n is real. This 0 because this is linear phase. And this 0 is because it is linear phase. So zeros will always be paired like this. Okay? This is 1. Because of the symmetry, this is the consequence of symmetry, because linear phase must be symmetry. If it is symmetric, then zeros will always be placed like this. This is number 1. Number 2 is what about if there is a 0 at -1? Okay, if there is a 0 here, I'm just saying, let's say what is at -1? The value of the function at -1, z is equal to -1, not 0. Let's say value of the function at -1 must obey this. So value of the function at -1 should be equal to -1 raised to the power -m h of -1. If m is odd, then h of -1 is equal to minus h of -1. Is this possible? Can x is equal to minus x? The -1 is to a minus m. If m is odd, h z naught, because -1 over -1 is -1. ठीक है ना? But can x be equal to minus x? Come on. No? X is equal to minus x 0. Yes. X can be equal to minus x only if, this is important, that if whenever, guaranteed, whenever m is odd, there will always be a 0 here. Whenever m is odd, type 2 filter. Whenever m is odd, when m is odd, once you have 0, 1, 2, 3. Let's say this is a type 2 filter. 0, 1, 2, 3. Okay? 0, 1, 2, 3 is a type 2 filter. It is guaranteed that every type 2 filter will have a 0 at pi because of this relationship. Because otherwise it will not obey -1. Okay? Because it must, this must be equal to this for any value of z. So -1 got to be 0. Okay? So what is the significance of a 0 at pi? What will it do to frequency response? A frequency response, if I place a 0 at pi, what will happen to the frequency response? It will touch 0 hoga. A 0 here means that frequency response will always touch 0 at pi. So then what? It means type 2 filter cannot be a high pass filter, because by virtue of its symmetry, a type 2 filter will always have a 0 at pi, means it will always touch 0. Means you cannot have a high pass filter as a type 2 filter. Here, this is the consequence of symmetry. Let me just repeat now. In FIR filter, our interest is only linear phase filters. Okay, linear phase. We want linear phase filters. A linear phase filters means symmetric or anti-symmetric. Okay. In symmetric, we have two types: type 1, type 2. In anti-symmetric, we have two types: type 3, type 4. Once we say symmetric, it means a lot. It means that the Z transform must obey this relationship. This relationship means that every 0, if you know a 0 in complex plane, you know 3 more zeros, guaranteed. Okay. Obviously, if there is a 0 here, so where will be another 0? Because iska 1 over this will be, if its magnitude is 1, it will be here, but just a conjugate here. A 0 on 0 will only have a 0 here, but a 0 here will have 4 of these. Okay, so let me, if I go and show you the MATLAB design tool and see how the zeros are placed. Okay.
Fourier transform.
जी
0 से 2 5 तक होता है.
जी जी वो रिपीट करता है.
जी ट्रांसफॉर्म में कांटूर जो होता है कि
जी जी
कांटूर. इसमें ये कांटूर से बाहर जा रहे हैं.
नो यूनिट सर्कल से बाहर जा रहा है. It is going outside the unit circle, zeros. But you don't worry about zeros. For FIR filter, you don't worry about unit circle. Remember why? Because stability is not an issue. ठीक है, because stability is not an issue, you don't care where your zeros are going. They will always go outside. Any zero inside means 2 zeros outside. Okay. So let's do this quickly. Show you. If you design toolbox, go filter design, go this. Okay, we say FIR, low pass. Okay, here is, what do you see? You see a 0 here means a 0 here, a 0 here, a 0 here. Always like this. Every 0 means 3 more zeros. Okay, every 0 means 3 more zero. A 0 here means 3 more zero. A 0 here means 3 more zero. A 0 here means only another 0 because it's on real axis. A 0 here means only another 0 here because it's on the unit circle. Okay, it's always like this. It is always like this. So let me try to say specify order. So it is this is, I have said order is 4, so there are 4 zeros. 1 0 is very close to the unit circle, so 1 over 0 will be very away from this. Okay, and the 2 zeros are here, so I know that this is so it's, if I plot its impulse response, this is the impulse response. This is the impulse response 0 1 2 3 4. Okay, so there are 4 of these. If I say 5, let me see if it is that or not. If I say 5, these are 5. You see, where is the 0? This 0 at pi. If you say 5, it will place a 0 there. It will always place a 0 at pi. Now interesting is, I don't know what MATLAB will do. If I force 5 and ask you to design a high pass filter, okay, let's see whether it complain or will try to do its best. And it'll try to do whatever it can. 5. It has shifted that. Oh, so this is what? It is not type 2. It has done what? It is anti-symmetric, you know. It's not symmetric because you cannot have a high pass filter with symmetric coefficients. So it's done that. Okay. So, but let me try to force it to use a window. I'm just trying to see if what it does. Oh, so I think MATLAB does not like it. Okay, so it does not like it. If I say I will learn about these techniques. I'm saying no, make it symmetric. Okay, it's saying no because high pass filter cannot have. You cannot design a high pass filter as a type 2 filter. Okay, this is, and remember all the other things which must, for example, if I increase its rate, let's say I say 10 is this, and I plot 0, what is this? Okay, again you see the same pattern. A 0 here, a 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, 0 here. So always be in this fashion. So whenever we are designing linear phase FIR filter, at least if for example, I give you a question in exam, you only know this. Can you plot other 3 zeros? Yes, you can. Okay, so for this, first 0 will be here. Okay, for this, a 0 here to make it linear phase. Then to make it real, you need to place a 0 here. And to make this 0 a linear phase, you need to make a 0 here. So you know this. If I tell you it is also type 2, then what? If I ask you this is type 2, then you know they got to be a 0 at pi. Okay, a 0 at pi. There will be always be a 0 at pi. Okay, because you want to design a linear phase FIR filter. Linear phase FIR filter is like this. Okay, so we know this now. Because of this, if Z0 is a 0 of h of z, then 1 over Z0 is also a 0 of h of z. Guaranteed. And if m is odd, then h of z must have a 0 at minus 1. Okay, must. So this is, if you have a 0 here, there will be a 0 here for type 1. And as I have already mentioned, if to make it real, you got to have a 0 here. If you have a 0 here, then you need to have a 0 here. So this and this and this and this will be complex conjugate of each other. So you get 4. And for type 2, they got to be a 0 at pi. Okay, and 0 at pi means it'll dip and touch. Then comes the type 3 and type 4. There's a negative sign. So negative sign means still we need, that is still true. A Z0 is a 0 of h of z, then 1 over Z0 is also a 0 of h of z. The only problem here is z is equal to 1. If you put z is equal to 1, let's do this, and minus 1, let's look at both. H of z should be equal to minus z raised to the power minus m h of z0. This negative sign is because it is type 3, type 4 filter. Okay, so find the value of the function at 1. Okay, at 1 the value of the function is minus 1 raised to the power minus m and h of 1. Okay, whether m is even or odd, 1 raised to the power something is always 1, so need not to worry about this. This you get h of 1. So when can this be true? H of 1 is equal to minus h of 1 is only true if h of 1 is 0. This is only true because x is equal to minus x is same. It is only true if h of 1 is 0. What is h of 1? What is h of 1? Where is 1? On this unit circle, where is 1? Anybody? On G. On the unit circle, where is 1? Here. So there will always be, whether it is type 3 or type 4, there will always be a 0 at 0, omega is equal to 0. So what does it mean? You cannot have what? You cannot have a low pass filter as type 3 and type 4 filter. You cannot have, no matter what. A low pass, you cannot have a low pass filter as type 3 and type 4 filter. I mean, an anti-symmetric filter can never be a low pass filter, guaranteed, out of question. Okay, this cannot be a low pass filter. Okay, whether it is type 3 or type 4. Now let's see about z is equal to minus 1. What do you get? Z is equal to, so h of minus 1 is equal to minus z, I'm sorry, minus 1 minus m h of minus 1. For m odd, this minus 1 and minus 1 will cancel or will make plus, so we are not interested in that. For m even, what will happen? For m even, h of minus 1 is equal to minus h of minus 1, which is only true if it is 0. So what does it mean? That if it is even means it is type 3, so there will also be a 0 at minus. Where is minus 1? At pi. So for type 3 you cannot either have a low pass filter or a high pass filter, no matter what you do. You can only have a band pass, band stop, those type of filters, but you cannot have a low pass, you cannot have a band stop, you can only have a band pass filter, because it will touch 0, it will touch 0, so both are zeros. Okay, so you cannot have a low pass or a high pass filter as type 3 filter. You cannot have a low pass filter as type 4 filter. Okay, and you cannot have a high pass filter as type. So this is about the linear phase FIR filters because of this. So if m is even, then h of z must have a 0 at minus 1. If z is equal to 1, must be a 0 for all m, for type 3 and type 4. So this is for type 3, they got to be these zeros are going to be there, but this 0 and this 0 will be there for type 3. Remember what is type 3? Anti-symmetric and m is even. This is anti-symmetric and m is odd. You can have you cannot have a low pass filter, but you can have a high pass filter. That's what the tool did. Once I forced it to design for m is odd, it designed it, because you can have a high pass filter in this type 4. So these are the consequences, that there got to be a 0 here. For type 1, no problem. For type 1 you can have any type of filter. Okay, so a filter, a 0 here is 0 here, a 0 here, a 0 here, but if 0 is here, there will be a 0 here. If 0 on the unit circle, there will be only a 0 here, a 0 here will be a 0 here. For every 0 in complex plane, there will be 3 more zeros. For every 0 on real, you will have another 0. Any 0 on the unit circle, there will be another 0. So you can easily plot this. For type 2 filter, this is true. There got to be a 0 here. Otherwise, you know what assuming Hn is real, okay, which we always assume. Type 3 filter, no low pass, no high pass, because a 0 here, a 0 here. Type 4 filter, no low pass, because a 0 here. Okay. So the linear phase FIR filters have all these 4 categories. So no matter you design, if you are using MATLAB to design, it will always design a linear phase filter. If you force MATLAB to design something which it cannot, okay, either it will complain, it will not design anything. You still need to know these things. If you are asking MATLAB, forcing it to no design, give me a high pass filter where m is odd, it cannot design that because of this reason. Right? So especially using the windowing method, which we'll study. So this is important, and that's what I have highlighted here. This I already explained the phase compensation, that I'll not cover this. Don't worry about phase compensation. This is the last topic which I intend to cover in this part of the course. This is filter designing, because then we know the complete deterministic signal processing. Minus, if you have a 0 at pi and minus pi both are same. Pi and minus pi both are in fact same. Pi, if you go like this is pi, and if you go like this is minus pi. So pi and minus pi are same. Okay.
For type 4 we have a 0 on pi.
Type 4 we have a 0 at 0. This is 0 at 0, frequency 0 है, 0 at omega 0. This is frequency. At 1 is the distance and omega 0 is the frequency because omega 0 corresponds to the DC value. ठीक है ना? So this is the frequency omega and this is the frequency pi, which is the highest frequency in the signal. ठीक है, हमें पता है pi is the highest frequency in the signal. If you place a 0 at pi, means once you plot the frequency response, the Fourier transform is guaranteed to touch 0. Okay? Because it touches 0, but the definition of high pass filter is you should have 1 at pi because this is the highest frequency content, you want it to pass. But if you are putting a 0 there, it will bring the frequency response to 0. So you cannot design a high pass filter because by definition a high pass filter is a filter which must pass the highest frequency content. Similarly, a low pass filter is a filter which must pass the DC value. If it is not passing DC value, it's not a low pass filter. Okay, so these are the frequency omega, but once we say 1 means a real axis, 1 plus 0j. Okay, once I say 1, it is 1 plus 0j. Once I say minus 1, it is 1 minus 1 plus minus 1 and 0j. So these are the terms. Okay, then now how do you design these filters? Okay, so we have learned about the analysis, the Z transform, the linear phase, the IIR, the pole zero plots, the Z transform, the frequency response, the difference equations, stability, everything. So now let's learn about how to go and design these filters, deterministic filters. And we already know the design is either you are designing low pass or band pass or high pass filter. Okay, so this is where pi is the highest frequency. Once we say high pass, it is this frequency response, ideal high pass filter. And you only plot from 0 to pi because you know 0 to minus pi is going to be the same. Two ways we know. Either you design an FIR filter or an IR filter. Given a specification, it's your choice. If you are designing an FIR filter, guaranteed it will be linear phase. No worrying about phase distortion. It will be stable, so you need not to worry about stability. But it will have more number of operations. You will require to do more number of operations. It will be computationally more complex. So FIR operations per sample will be more. Will be very high order. So this is the price you pay. If you are designing an IR filter, it will be shorter than guaranteed for FIR filter. It will be very small, it's a less number of computation, lower order, but more susceptible to quantization. Quantization means if you are quantizing your coefficient to 8-bit, okay, so the pole will change its position. Means if you have infinite precision, you design a filter in MATLAB, you have infinite precision. MATLAB will in double precision arithmetic, it tells you the pole is at 0.93126157. If you look at the number, it's a double precision floating point number. But if you are using a DSP, which is only 16-bit DSP, remember those of you who have taken the course, you need to change it into Q format. So you truncate it, you only keep 16 bits. Once you are doing that, in fact you are changing the location of pole. Once you quantize a coefficient, what are you doing? You are mapping it on a grid. Okay, if let's say they are 4-bit means there are only 16 possibilities. So for this pole has only 16 possibilities to occupy. So the pole position will move to a legal 4-bit location. If it is 8-bit, they are more, but definitely the pole will move. Once you convert a double precision number to a fixed point number to a 8-bit or 16-bit number, guaranteed the pole will move. So what will happen if pole will move? The pole is basically defining what? The frequency response. If pole moves means your frequency response will change. Number one. Number two, in many circumstances, the poles are very closer to the unit circle. Literally sometimes the pole will move outside the unit circle. In many circumstances, usually the poles are placed to bring the frequency response to closer to higher. A pole may even move outside the unit circle. So that is what it says. More susceptible to quantization and rounding errors, because a few poles are controlling everything, the stability and the frequency response. but less number of multiplication for sure. So it's your choice whether you design an FIR. Traditionally, you can always find out that what people do in communication, what they do, in speech, what they do, So you can figure out that, okay, people use here FIR filters, here IR filters. But we also know that ideal is not possible. Ideal, though you want always to design, and this is the specification of a filter, irrespective of the fact whether you want to design an FIR filter or IR filter. Ideal is this. It should be 1 and then it should just drop to 0. This is for a low pass filter. And you say this is my cutoff frequency. I don't want to see anything after omega c, and I want everything to pass from 0 to omega c. And remember, because on the other side you have the same thing, so it's only plotted from 0 to pi. Now you can never achieve the ideal frequency response. So you have to give some leverage as design parameters for the filter design package to design something for you. So the more flexibility you give here, the simpler will be the filter. Okay, less complex will be the filter. If you start tightening up the constraints, you will get more and more and more complex filters. For example, you say, okay, I am fine if it is not 1, rather it is 1.1 and 0.9. You say, I don't mind. If it is not exactly 1, but my frequencies, the pass band frequencies are just changing from 0.9 to 0.1. But you say, no, I want it to be more precise. So you may say, I want it to be 1.01 and 0.99. So you can say that. You can give specification in terms of this. So you specify this delta 1. It can go above or below delta 1 from 1, and as you keep tightening up this, the filter will start getting more and more complex. Similarly, it will never be 0 here. So you need to give it some room to be very close to 0. This is delta 2. You may say it should be 0.001. It should be 0.001 means it should be divided by 1000. All the amplitude should be divided. You say 0.00001 or you say 0.001. So it's up to you, but you can just say delta 2 should be this. Okay. This is the second design parameter. The third design parameter, it will not exactly fall down to 0. You need to give it some space here. You say, okay, from here it should drop down. So this is a transition band, and you are saying, I will accept omega pass and omega stop. Omega pass means all these frequencies must pass, and omega stop means that no frequency after this should pass in strict sense, should never be greater than delta 2. So you want those frequency contents to drop down to 0.001 or lower values. So these are the design parameters. So you need to specify delta 1. So you want your tool that your frequency response should never go above delta 1, 1 plus delta 1, or below 1 minus delta 1. Then it is omega pass. This is omega pass, and this is omega stop. Okay, omega pass and omega stop, and this is delta 2. Your frequency response should never go above delta 2. So you have to give all these things. These are the design parameters. Once you are designing a filter, you need to specify delta 1, delta 2, omega stop, omega pass. Okay, and then if it's just MATLAB, you let the MATLAB design it for you. But if you are doing it yourself, let's see how you do it here. So this is pass and stop band. Edges are omega p, omega s. Maximum pass band ripple is delta 1. Minimum stop band attenuation, usually it is written as minus 20 log base 10 delta 2. It is given in terms of in dBs. So this is whatever value you have, 0.001, you take log base 10 of 0.001, and then you multiply it by minus 20. For example, it is 0.001 is 10 raised to the power minus 3. So log base 10 of this is what? Minus 3. So minus 3 by 20 is 60. So 60 dB of attenuation is equivalent to divided by 1000. Okay. If it is 4, it will be how much? 80 dB. So 80 dB is 0.0001. So once I say 80 dB down, it means divided by 10,000. So all the unwanted frequency contents will be divided by 10,000 substitutes. 10,000 time you are reducing them. 80 dB. So 80 dB is very good. 60 dB is good. So similarly, I can have -5 is 100 dB. So 100 dB down means this much. 0.00001. Right? Oh no, sorry. 0.00 is an extra 0. This much. Okay. It is 1, 2, 3, 4, and 5. 100,000 times. 100,000 times means -100 dB, -200 dB. So you can similarly, you always need to relate this, because usually it is, the plots are given in dB. So once you say 60 dB, you must know it is divided by 1000. Once you say 80 dBs, you know it is divided by 10,000. Once you say 100 dB, it means it is divided by this number. So you must always know this. Okay, so it is because it is given in dBs. So here is, and usually delta 1, delta 2, or 1 plus delta 1 and 1 minus delta 1 is also given in 20 log base 10 dBs, but this is important, delta 2, 20 log base 10 delta 2. It is in dBs, okay, this much down. So these are the design parameters. If I go to MATLAB and show you this, so this is really what, once you say specify, you say minimum order, and you want to do a design, let's say an IR. This is what, so in MATLAB you need to provide it with the A pass and A stop. This is in dBs. This is delta 1 and this is delta 2, 80 dB and 1 dB. Okay, this is the sampling frequency, because it's better that you give sampling frequency, and in relation to sampling frequency is 2 pi. So you specify 2 pi, and then the F pass, the frequency you want to pass is omega p. This corresponds to omega p, but it is given in hertz. Okay, so that usually people prefer, because they know the sampling frequency, they prefer to use in hertz, though it's a digital frequency. So it is, if 2 pi, you can always calculate this and this. So this is omega pass and omega stop, and these are the specifications. If you change these specifications and you say minimum order, MATLAB will try to compensate. Okay, you can change this 80 to 100 dB or to 200 dB. Filter will start getting more and more complex. You change it to 60 dB, it will spend less number of coefficients to give you a filter. Right? So these are, this window on the right hand side is the design parameters. You specify design parameters here, and as you can see, it can, you can give your specification in hertz, in kilohertz, in megahertz, in gigahertz. If you come here, you can give the in dBs or squared, just magnitude squared. It's up to you. So now knowing this, this is how the specifications are given. So usually you will be asked to design a filter which can, remember this 1.01, you want these frequencies, 400 hertz, 2 pi fa. Okay, 400 hertz. So if I draw this, you want up to 400 hertz. You want it to never go below 0.99 and above 1.01. This is how the specifications are written. So you don't want that. Then you are giving it a transition band to fall down to omega stop from 400 to 600 hertz. So you say 600 hertz. It should fall down to this value, and then you want it to be 0.001, which is 60 dB. You want it down to 60 dB after 600 to 1 kilohertz. So 1 kilohertz is pi. 1 kilohertz, you specify pi. So now you know that these are your design parameters. So you ask MATLAB to design this filter. You can always convert these into small omegas. Okay, the digital filter specifications. And what is that? If this is your 1 over t is 2 kilohertz, So pi will be this. So you know the relationship that small omega into t is capital omega into t is small omega. Okay. So you can find out from omega p you can compute small omega p. From omega stop you can compute small omega stop. How? By multiplying it with capital T. What is capital T? It is 1 over 2000. So divided by 2000 you get the omega pass is 0.4 pi, omega stop is 0.6 pi, and 1000 is the pi. So these are the digital specifications. So you can always convert this to these specifications, and then you decide whether you want to design an FIR filter or IR filter. Let's say you choose to design an FIR filter. Say I want an IR filter. Okay. So interestingly, discrete time IR filter design is done using analog filter technique because it is such a mature science. People have spent years to find out ways of designing IR filters. They do it in HS. Okay, so IR filters are designed in Laplace domain. So you can find manuals and books on IR filter. You give it specification, open the book, it will give you a transfer function, H of S. So people, instead of wasting time in inventing ways of designing IR filters in discrete domain, they said, don't worry about it. Just open the book. First convert the digital specification to analog specification because you know the sampling frequency. And then what you do is open the book, find an H of S. Use a method which is already there for designing an H of S. Design H of S. Then convert this H of S to H of Z to a difference equation. Okay, this is what is done. So the IR filters are designed, analog IR filter design methods have simple closed form solutions in terms of H of S. You can write it as a transfer function. Design examples have existed for years. So direct design of IR filters has traditionally been avoided for these reasons. Right? And direct design of FIR filters you always design because it's not, you don't design them in analog domain. So this is what is done to design an IR filter. You have a discrete time specifications, you convert them to continuous time specifications, you go design a filter in continuous time specifications, and then you convert it to discrete time specifications. What you have to ensure? You have to ensure a stable filter here in continuous domain must translate into a stable filter in Z domain. What is a stable filter in S domain? All the poles must be in left hand side S plane. And what is the stability in Z domain? All the poles must be inside the unit circle. So this is one. The second is that if your filter is specifying, if your filter is meeting your design constraint, if your filter is meeting the design constraint in continuous domain, it must meet the specification in discrete domain as well. It should not happen that though you have spent a lot of time in designing this, but once you come from here to here, it no more meets your specification. If it does that, there is no point in going through all this. So you have to make sure a stable filter here means a stable filter there. Meeting specification here means meeting specifications there. So this is what it is. So all the poles on the j omega axis in S plane means this, but pole in the left hand of the S plane corresponds to pole inside the unit circle. So if a pole exists here, it should map a pole into the unit circle, because in HS stability means a pole in left hand side S plane. So hence stable and causal continuous time filter will produce stable and causal discrete time filter. This is what you need to guarantee. A method must guarantee this. So these are three methods of designing IIR filter in continuous domain. They're called Butterworth filter, Chebyshev filter, elliptic filter. Okay, those who have taken analog filter design course, you must have learned all these. That these are the three ways of designing a continuous domain IIR filter. Okay, using actual analog circuit components. It'll give you a transfer function, then you figure out capacitor, resistor, inductors, and you put them together to make an analog filter. Okay, but our interest is not in those components. Our interest is in H of S. So Butterworth. Let's see what is a Butterworth. What are the differences? A Butterworth filter is a filter where people have come up with ideas that the frequency response, again in continuous domain, is a monotonically decreasing function of frequency. A monotonically decreasing function means it will never, at this point, this point will never be greater than this point. At this point will never be greater than this. So it monotonically will do a very smooth frequency response. It will not ripple. It will just go like this. Okay? It will not ripple. So don't allow it to ripple. So people try to find a mathematical formula. Those who were inventing these filters, they say, let's try to find a mathematical formula for a function which is monotonically decreasing in omega, and then try to come up with an H of S which generates this H of j omega, and then try to make sure that it is stable. Okay, this is the Butterworth filter. In Chebyshev filter, they said, let's allow some ripples here. Chebyshev type 1. Chebyshev type 2 is allow some ripples here. So people said, no, let's allow some ripples in the passband. So what do you get? And I said, okay, what if instead of allowing ripples here, you allow ripples here? What do you get? So Chebyshev type 1, type 2. And then elliptic filter, they say, let's allow ripples in passband and stopband. So ripples here and ripples here. So you don't care if it is meeting specifications. You say, I don't care. All I care is that it must meet my specification. If it is going up and down, I don't care. Right? So this is these are the three techniques which are used to design an IER filter. If I go back to MATLAB, though we'll learn how to look in. Once you say IER, MATLAB will say, obviously MATLAB will give you more ways, but it says Butterworth. You want to design a Butterworth filter, a Chebyshev type 1 filter, a Chebyshev type 2 filter, an elliptic filter, and then there are a few other methods, but this book covers these three methods. The important is the differences. Let's first ask MATLAB for these specifications. Ask MATLAB to design a Butterworth filter, a smooth H exponential j, H j omega. So you say design a Butterworth filter. So MATLAB will come back and tells you that, look at the response. Okay, it's minus 500 dB. Okay, so it'll be, but it'll very smooth. Okay, so MATLAB comes and tells you that for these specifications, MATLAB will take 31st order IER filter. 31 order means there will be 31 poles in the system. It says 31 poles. You can get B's and A's, but this is what MATLAB tells you. You say, okay, I will allow some ripples in the passband. So you say, let me try see what MATLAB does if I design a Chebyshev type 1 filter. I say design. So MATLAB comes back and tells you that a type 1 filter can be designed using only order 13, means only 13 poles. Now 31 poles have reduced same specifications, but has reduced. It's a significant reduction in complexity, that only 13 poles. You say, what if I say Chebyshev type 2? And you say design. It says a type 2, remember you see ripples here, because in dBs these ripples are more profound. It's more significantly seen visually because of the dB, but here as you can see it is at minus 80, it will never go above minus 80 dB, because that's what you said, minus 80 dB, 0.0001, right? But then you say give me elliptic, okay, elliptic filter, and you say design 8. The same filter, instead of 31 coefficients, but now there are ripples. You can see there are some ripples here and ripples here. 8 means 8 poles. You can go look at the pole zero plot as well, but these are the, and we have already seen this, 8 poles, 8 zeros. So this is an elliptic filter. Okay, you can try because MATLAB has provided you with some other, let's say maximally flat, I don't know what will it do. So let's see, it's 10th. Okay, it's a 10th order. If you are saying maximally flat means it'll try to make the frequency response smooth, but it is still more than 8. Then you say it's a least pth norm. It says 8. Okay, this is I think the H infinity filter. So this says 8, and then you say the last one. So 10th. So apparently the elliptic filter is the simplest to implement, which implements this spending the 8th order filter. So this is how you need to choose one of these methods, either the Butterworth, but remember this will give you an H of S, and then you need to convert that H of S into H of Z. We'll continue learning this, but let me just show you what you get, and then what do you need to do to, these are the method, but I only want to show you what you get once you design a filter. Once you design a filter, end of the day, it will give you a transfer function which looks like this. Okay, and H of S is equal to 0.12093 divided by, these are the S square plus S plus this, so 3 S squares. 3 S squares mean 2, 2, 2, 6. It's a 6 poles. So these are the 6 poles, 1, 2, 3, 4, 5, 6. But you don't need H of S, you need H of Z. So you convert, you use the transformation and convert this H of S into H of Z, and this is H of Z. Same filter. And you like it because this is a second order, 3 second order sections, which is again 6 poles. It also has 6 poles. Okay, but this can be easily then implemented. Okay, so we will learn how to first compute H of S. Okay, then there are established methods, and then you take H of S, and it is not only true for digital filters. Any analog system with a transfer function, whether it is a control system or any system where you can find old radar manuals, you open that, they will give you the transfer function, that this board has this transfer function. I have actually done this, that if you look open, you will find H of S are given. H of S is, they say this is the transfer function for this board, transfer function for this. You can throw that board away and in fact convert it into H of Z, and H of Z means a difference equation. A difference equation means you need to digitize your analog signal to X of n and then pass it through a difference equation, get Y of n, and if you need to convert it back to analog. So you can discretize any existing analog system with a transfer function H of S to an H of Z, which is with a computer program. So any analog system can be converted into a computer program, almost satisfying the same specifications. So this is, I intend to just cover this, and then we'll move to the other part of the course, the filter design, so that you know that this is how the filters are designed.